All right, so ladies and gentlemen, welcome to the second day of talks called CIIRC Annual Colloquium on Research Results. Each head of the department will manage his own time slot and is responsible for finishing on time. And now let me ask Professor Hlaváč to introduce his department and to invite his speakers.
Okay, so I'm pleased that we can report our results in this meeting, which I find very useful. So I'm surprised that only 23 people or 30 people are logged in here now today. Robotic and machine perception departments consists of 3 groups. One of them is called robotic perception. Second one is called applied algebra and geometry, and it's headed by Tomáš Pajdla, whom you can see in the picture. And the third one is headed by Libor Přeučil. All these groups are financially independent, so it means that also the heads of that groups are very, very independent. So my role at coordinating these 3 groups is only kind of methodological, nothing else. Okay, so first speaker, I think it's Josef Šivic, start.
Thank you, Vašek. I'm working on sharing my screen. Do you see my screen now?
Yes. We see both you, we hear you, and we see your screen.
Okay, that's great. So I will, in my short slot, what I want to share with you or talk about this paper called CosyPose, Consistent Multi-View Multi-Object 6D Pose Estimation. And it has been published at the European Conference on Computer Vision. Many of you know. For those who don't, this is one of the top computer vision conferences, top 3. This one is held every 2 years. And just to illustrate, ECCV has had about last year more than 5,000 submissions, and about 1,300 were accepted, which is about acceptance rate about 26%, and it's quite big with more than 1,300 papers. And I've chosen this paper because we also won a competition with that, which I will tell you about. So the goal of this work is given a set of input images, 1 or more. Here we have 4 images of a scene and a set of known 3D models of the objects which we observe. So we assume we know 3D models of the objects of these different electrical equipment in this case. And given these images and the known objects, we can recover the 3D of the scene, so which means the 6D pose, the position and orientation of each of these objects in the scene, and together with that, the camera poses. So here the black parts which you see, these are the recovered camera poses. So this is the setup, and so this is one of the old computer vision problems, and it's interesting one because it has these applications connected to robotics. So imagine if you want to now, you observe a scene with a camera and you connect it to a robot, and you now want to say, I have this 3D, I have this object, which I want to pick up that object from the scene specified by the CAD model, maybe on a line, you want to pick up all these objects. Then this method can automatically recognize it for you. Is this object here? And then because you know its exact position and orientation in the scene, you can just plan very easily a motion. This is in simulation to grasp this object. And note, for example, this problem is very difficult because you can distinguish this particle plug from another similar one, which has like 4 components, a bit bigger. So it's a hard problem because the objects are self-similar and textureless. So we developed a new method to do that. I will not go into details, but the main innovations are combining powerful neural network representations with multi-view constraints. That's the first innovation. And the second one is that we really pushed idea. This has been around, but we really pushed it. The idea of training from synthetic data, because we know the 3D models, we can really generate many synthetic examples and really make it work well. So one has to really sort of we call data augmentation, to add additional noise so that they match what can be possibly observed in the real input image. And I will spend the rest of the time just showing that it works very well. So it can also work not with multiple, but only single image. So this is the top is the single input image. This is the predicted poses of the objects overlaid over the input image, the CAD models colored, and here is the 3D visualization of the scene. So from a single image, despite you can notice the occlusion of this object by this object, yet we recover their poses well. Here is another example. These are more difficult, I would say, because these are really self-similar objects, textureless, yet we can recover and distinguish these different objects from each other. And it's quite precise. You can see that this object is plugged into the other one, and it seems to plug quite well in the scene. And here is another example of a scene, also with many objects occluding each other. And finally, even objects which are very similar, these are the same objects, we can still deal with the situation. We missed one of the objects here. You can see the cup in the middle, but the rest are recovered well. So it works very well, and it works. We went into competition on 6D object pose estimation, which is on 7 different data sets, and we won the overall best method on this, significantly outperforming the other methods. Just to illustrate that, I have the plot here. These are the best other competing methods. This is some kind of accuracy higher is better, and our method is outperforming them significantly in these different setups. And what's interesting is that this is our bar here. It performs similarly to methods which use depth sensors for the same problem. So, which was surprising to us, but you can achieve similar accuracy. And then if we use depth as well, our method can work even better. And I encourage you to use it in applications. We are really looking into using this in robotics setups. This is an example of a robot observing the scene. We can recover the relative pose of the objects between the robots so that we can then plan a grasping motion. And here is just a preliminary example. We're just putting together a team at different in collaboration with Paris and in Toulouse to really plug this method into a robotics setup and use it in real applications. And we have a similar or the same robot here in Prague on the 3rd floor, and it'd be great to collaborate to really make this happen. And that's all from me. Thank you very much for the attention.
I thank you, Eugene, for your presentation. One question, please.
Maybe I can ask. I didn't understand whether you may have also multiple objects of the same type, or if you know that you have exactly one object of each type.
No, we can have, so this is an example, the cups on the side. I think here we can really deal with multiple objects of the same type. So these are the same objects and we can still recover them in the scene.
Okay. And how precise information about objects you have? For example, you have like full 3D description of the object. So if it's turned from different side, you always can match it with 3D description, right?
Yes. Yeah. So we assume a known 3D model of the object. So we would have to go and capture, and that's one of the bottlenecks at the moment. One limitation, it takes quite a lot of computing power to train these models. Apply them is quite easy. You can do it almost 10 frames a second. And the second limitations, but it takes like 2 days to train. And second one, that we need the quite accurate 3D model of the object. But we are working on improving on both those aspects. But still, I think in the current setup, we think can be still useful.
And how much time you need in online behavior when you grasp objects? Is it like in second, or does it take more time?
So this is an iterative method. So I think one iteration takes about 1/10 of a second. In online method, I think we can run it in this way. But I think exactly for robotics, we are working on plugging in with some kind of a tracking method, some Kalman filter, so that we can really, operate in a much faster speed. You can put it in a control loop, this approach, and also make it back propagable so that we can really, I think that was in the slide, we can really have now fully trained
Okay, and now you have to unmute yourself.
That was the answer to the question. And now comes the next speaker, which is Tomáš Pajdla.
Okay, very good. Thank you very much for the introduction. And I will present a paper which is a collaboration between ETH and the CTU. My former PhD students, Čeněk Albl, Zuzana Kukelová, and my current PhD student, Michal Polic, and Viktor Larsson and Konrad Schindler. And Čeněk, Viktor, and Konrad are at ETH currently, and all other people are at the CTU. This paper, from 2 rolling shutters to 1 global shutter, has been presented at the CVPR 2020. It was an oral. A CVPR is another primary conference on computer vision, and this paper was among those 5% of all out of more than 6,000 submissions to the conference. So this is about global shutter and local rolling shutter. So on the left panel, you see what happens if you move a camera with a global shutter. So the images are somewhat blurred, but they are geometrically correct. On the right-hand side, you see what the rolling shutter is doing. And we see that these images are a little bit less blurry, but they are kind of geometrically distorted. And the reason for this is that for rolling shutter, images are acquired line by line. So it's kind of like moving a scanner, flatbed scanner, and every line is exposed and taken at a different time. This is an important technical method which allows the serialization of data flow and efficient implementation of this camera technology. On the other hand, it brings distortions for moving cameras. And currently, this is a prevailing method of image acquisition. It's in many, that's a billion of modern cameras, particularly cellular phones. And it has the same effects like, these geometrical effects, like camera translation brings certain slanting of closed objects, camera rotation brings certain bending of objects, and if you have very fast moving objects, then you may see some very strange effects. Now, the question is, and our paper is about how we remove the distortions. And this will be shown by the next presentation, which Čeněk gave at the CVPR. So I'll start.
My name is Čeněk Albl, and I will present our paper.
Čeňku, can you show your video of your face?
Camera systems.
No, he can't.
In summary, we show a novel camera configuration that requires just a simple change to existing multi-camera systems. Such configuration allows to utilize the rolling shutter distortions in a way it was not possible before. Most importantly, we can compute the motion of the cameras, remove the distortions, or compute the depth of the scene. We present multiple algorithms that leverage such camera configuration and are extremely efficient and robust. The core idea for the camera configuration comes from the fact that many devices, most prominently smartphones, come with 2 or more rolling shutter cameras. When such cameras capture images while the device is moving, the images become distorted, which causes visual as well as computational issues. The common characteristics until now is that all the cameras scan the image in the same direction, for example from top to bottom. This causes the distortions induced by the motion to look the same. Instead, we propose to roll the shutters in the opposite direction, such that the distortions are as different as possible. Our algorithms can then utilize these differences to compute the camera motion, remove the distortions, and other things which will be shown later. First, we take a look at the most general case, where the motion contains both rotation and translation. We start by finding correspondences between the images. In this case, we need 5. Next, we form a system of algebraic equations. Then we solve those equations using our Grabner basis-based solver. Note that this solver is very fast and therefore suitable for both robust and real-time estimation. As a result, we obtain the angular and translational velocities. If we then want to remove the rolling shutter distortion, we need to know the corresponding pixels in the input images. Standard techniques such as optical flow can be employed to obtain these correspondences. In general, each pixel was exposed at a different time, and therefore different camera position. This allows us to compute its depth, and create a depth map for each image. Finally, we can use these depth maps to reproject pixel colors to create an undistorted image. Now we take a look at the case where rotation motion is dominant, which is common in handheld photo or video. This time, things get much easier, as we only need two correspondences. The system of equations becomes much simpler, and we show how to solve it using a recently published solver that only takes around 4 microseconds. Once we obtain the angular velocities, we do not need to establish the dense correspondences, but instead we have a mapping to warp the entire image to an undistorted image. Here is a video sequence showing the undistortion in real time. We pause the video at moments where the distortion is significant. On the top, you see the two original rolling shutter images. Bottom left is our undistorted result, which you can compare with the image from a global shutter camera on the bottom right. We can also warp both input images and combine the outputs such that a more complete image is formed. Note that even though the stitching is not perfect and some artifacts are still visible, this is without any kind of post-processing, just the pure geometrical warping using the computed motion parameters. It is worth mentioning some other results we can get using our methods. One of them is using the undistorted sparse correspondences in Structure for Motion Pipeline, where they clearly provide much better reconstruction than those coming from the rolling shutter images. This is especially apparent on the nearby objects. As mentioned earlier, with translation motion, we obtain depth map as an intermediate product. Since the depth map is computed from the differences in the images, it will be most accurate at the top and bottom of the image, where the differences are the largest thanks to the opposite shutters, and it degrades towards the center where the image rows were captured at the same time and look identical. The depth map will not be as precise as from a stereo rig, but it offers a reasonable depth estimation in a place where such pair of images with identical shutter direction would provide no depth information at all. Finally, we show the potential for many existing camera setups where one of the cameras has a zoom lens. As a demonstration, we show a result where one of the images is cropped and only a zoomed part is used for the computation of the motion parameters. The motion parameters can then be used to remove distortions from the entire larger image, and the results look excellent. Thank you for your attention, and for more information, please visit our website.
Okay, so this was Čeněk's presentation, so I'll be very happy to take questions. Thank you.
Okay, your questions, ladies and gentlemen.
If I may ask again, so there are only static objects on your recordings. So, for example, no person moving, no car moving. Is that different in the presence of dynamic objects as well, or you can recover the same information from the static ones that are behind the dynamic ones, or how is it?
Of course, this is in some sense static scenario, but everything what is static and dynamic depends on the time scale in which you are working. So this image acquisition is relatively fast. So you can think about depends what is the frame rate, but with a standard frame rate we are talking about tens of milliseconds, right? So if your objects are not moving very, very fast, then this will work for them as well. If they are moving fast, compared to the scanning of the image, of course, there will be artifacts.
Okay.
Okay, thank you.
Thank you for the answer. Let's move to another speaker. Yes. So the Vladimir Petrik takes over, and Zattler will Torsten Zattler will recover. Yeah. Okay.
So just please confirm that you see my screen.
Yes, we do.
Yeah.
We hear you. We see the screen.
Thank you. So I will present the paper Static Stability Analysis of Fabric Strip Folding, which was published in Transactional Mechatronics. This is a joint work with Vladimir Smutny from CIIRC and Vila Kirky from Aalto University. And the goal of this work is to analyze the folding motion. The folding motion can be characterized as gripper grasp the short edge of fabric strip, as shown in the right top figure, and follow a pre-computed folding path. The goal, or the expected state, is shown in the bottom figure, where the both edges are aligned at the end of the folding motion. There were many methods proposed in the past to solve this problem. For example, the triangular path, where the gripper follows just path which resembles a triangle. And this was derived from the assumption of infinitely flexible garments. Or there were circular paths, designed from different assumptions, or R-shaped paths, which takes the garment bending into account, and design paths for the specific garment. There were other trajectory optimization formulation of this problem, where the predictive simulation was used to optimize the trajectory offline in simulation and then applying to the robot. Or as everywhere else, there were also some deep learning techniques to train a policy to fold the garment. Goal of our work was to use static stability to show why fabric folding is difficult and why we need so many different methods to perform the task which we as a human are solving every day without any problems. So to answer this question, we use a static stability analysis, and for that we need a model of the fabric. So we approximate fabric by homogeneous continuum mechanics model, which was parameterized by a single parameter, which represents the bending stiffness ratio. And as an example, you can see the folded state on the right picture, which is the same length strip, but with a different bending stiffness ratio. So the expected folded state is different for different parameter. And these states we can simulate using finite element methods. And in addition, we can check the static stability of each state by looking at the condition number of stiffness metrics during the simulation. So that's what we did, and I will show the example of static stability for simple horizontal gripper motion, where the height of the gripper over the ground is constant and is moving from left to right. At some point, which is shown on the right picture here, the strip starts or loses its static stability and starts to behave dynamically, which is shown with the red color on the right picture. So this fabric strip will fall down dynamically and will be stabilized by the ground at the end. This motion is dynamic and therefore requires a time to simulate it, time variable. After ground stabilizes it, it's static again, as shown with the green color. The problem with this dynamic motion is that it's hard to recover back after there is this collapse, dynamical collapse. So it's hard to plan accurate trajectory, which would result in the accurate folding at the end. So there is this static instability in manipulating these fabric strips. We perform experiments to check if our simulation or this behavior, the dynamical behavior, is observable in reality as well. And we measure various materials for different heights of the gripper, as shown in the right figure. So that was the motion performed by a robot. The robot and camera cell were calibrated, so we were able to extract the position of the critical point, which is the point where the fabric lost its stability. And we compare the simulated and real data, which is shown in the plots here. So the simulated data are the dash is the solid line, and the real position of critical points are shown as the dots. If our model would realistically model the fabric, the dots would be lying on the line or on the curve, which is not the case here. However, the model always underestimates the value of critical point because the model is perfect and approximates the fabric by continuum. We think that, or we believe that this missing effect, which is causing this shift of the real fabric behavior, is caused by ignoring the friction between the individual threads of the fabric. Nevertheless, this fact that the model always underestimates the value of critical point can be used in the analysis of the strip folding path. So that's what we did. We followed the path for the folding in simulation and find the position where the system lost its stability, static stability. And this situation is shown with a black color for each pass separately. So if we would continue the motion for the triangular and circular paths, the fabric strip would fall down to the right, would collapse to the right, which is hard to recover. For the R pass, the situation is different because the R pass is actually balancing on the edge of the stability. It's something we analyze in the paper, that if we add the disturbance to the left, then the fabric would collapse to the left, as shown with the red color. If we add disturbance to the right, it will collapse down to the ground. However, this is just for the ideal model. So if there is perfect continuum. If we approximate this internal friction by some negligible damping, it will stabilize the strip for this R path. But it will not influence or not significantly influence the triangular and circular path. That shows that this R path is suitable for folding fabric strip folding, but would not be good enough to fold perfect continuum materials because any disturbance would result in a bad folding. So to conclude, we studied singular fabric strip folding. We showed that there is an instability in the folding process, and that instability makes it difficult to design a folding path. And we confirmed that this instability by experiments and showed that R shape can be used to fold fabric strips. That's all for me. Thank you. Professor Hlaváč, we don't hear you. Your microphone is mute.
Thank you. I thank you to Vladimir Petrik, and questions, please.
I have a question, Jan Behrens here. Would it be possible to use your method in a reactive controller, which could then maybe even recover for other unexpected cloth?
Yes, this method was in COMSOL simulation, which is quite slow. So not in a high frequency loop, but otherwise, yes.
So the next speaker is Jan Behrens. Jan, can you start, please?
No. Okay.
Yes, we see that.
It's there. It's okay.
Okay, good. I present today work done with Kala Stepanova and Robert Babushka. The paper was presented on CIIRC 2020. It's called Simultaneous Task Allocation and Motion Scheduling for Complex Tasks Executed by Multiple Robots. I introduced planning and scheduling for robots. We have here multiple robots, which you can see on the right, which work on a common task. So they have a shared task, and we want to plan their schedule to improve the make span. Thereby, it's important that we avoid collisions. And the tasks also have constraints. So basically what you see here on the top is there's some bolts inserted and afterwards they are glued. And this partial order from the task has to be maintained. And between the tasks, we have to generate the motions which connect all those tasks. The decision variables are mainly the task allocation, so which robot is doing what, the variant selection, so sometimes there are different variants to fulfill the same goal, and the ordering of the tasks and the exact timing. We do this by a compilation of the problem to a constraint satisfaction problem and optimize the whole scenario by repeated satisfaction. So complex tasks, I will define the complex tasks. So complex tasks are combinations of multiple subtasks. An elemental task is fully specified in deterministic robot program. So that means either the right or the left arm is doing something and it's completely deterministic. Complex task, as defined in the literature, is a task which has multiple decompositions into elemental tasks, so you can decide something. And it can be, these elemental tasks can be assigned to different robots. More complex is the scenario even because the utility or cost of the actions or the robot schedules depend on the actions of the other robots. In this paper, we introduced a new type of task, which is an extended task where we analyze or have a task which includes a bigger motion, not just drilling a hole, which is quite constant, but it's a motion. So we incorporate the time dependency to create tighter schedules. We have like a profile over time of the voxels which are occupied. Here you see in a similar manner how the profile looks like. So we have different for each over the trajectory, for each time interval, different voxels which are occupied, and that's for the whole task. Because the robot is a dynamic system and it would need some time to stop, we always occupy some space in front of it. So here we have like occupied always from the current time step the volume plus something in front of it, so that the robot could always come to a full stop if necessary. Here you see again how the voxels are, the robots are represented with their voxels, and here they are not in collision, but you see here two different tasks, like two different line motions, for example, and we go through the first line motion and we check for each segment if it's colliding with something. This segment is colliding with these here, and we have different methods to compare these, and when we detect that there's something colliding, we add a constraint like this, that those intervals, this here and this whole thing, may not overlap. We compile the whole model, which I don't go into detail, but we have a task model here where all the tasks are compiled, and we have a robot layer where all the robot trajectories are represented in constraint variables. I go over this quickly. Yeah, the intermediate motions is interesting, are generated using a roadmap, so the robot can freely move in this graph which you see above here, and the extended tasks which we introduced in this paper are then connected to this roadmap and can be executed here. I show here the solution quality which we can get with our method on the left side. Like both robots will have to make a line here in the middle, and without our method, the other robot can only start when the first robot is retracted, and in our proposed method, it can already start earlier and it will not collide. This can save time. Okay, and our method is kind of an anytime method, so the solutions are generated quite quickly. After seconds, we have the first, but the first solutions are not of high quality. So you see here the first solution, which takes quite a lot of time to fulfill. On the right side was the solution after optimization. I play the video once again. On the right side, you see optimized order of the interaction of the robots, so that you get way quicker make span. Thank you for your attention. I'm happy to take some questions. I don't hear you, Vasek.
Questions, please. So my question, Jan, so you did your work in simulation only. Why did you do so when you have these robots available in real here?
It was a matter of time, but it's definitely on my to-do list to do it in real. Like in simulation, we have also more control and better logging, but it's definitely on the list to make it more convincing.
Okay. Thank you. So let's move to the next speaker. It's going to be Thorsten Sattler, third attempt. Thorsten writes that he's now able to share his screen.
Yes.
So let Thorsten tries, and if it fails, yes. Okay, we see the screen. I don't know who is presenting it, but we have it.
Okay, 3 times is a charm. So this is joint work with Tomáš Šivic, Viktor Lawson, and Mark Polyface from ETH, and this was presented at CVPR 2020 as an oral. So same conference where the paper that Tomáš presented was presented, and it's about camera calibration. So the motivation for this is was the first work that the PhD student who worked on this paper did, Tomáš Šivic, and was about building a 3D reconstruction system, a system that runs online on a mobile device. So it takes images and builds a 3D model. Here's another example of a 3D model. You should be all familiar with this. And so this was captured from like maybe 100 images or so. And in order to get good 3D models, you need to have a good camera calibration. And this is a very traditional problem in computer vision. So camera calibration is essentially finding a mapping that maps from a pixel in a 2D image into a ray in space. And the traditional way is to compute fit parameters of some parametric function that, given to a pixel position, gives you the ray direction. And the parameters are typically focal length, principal point, some distortion parameters. So you typically have tens of parameters. And those models have been used for decades. They work well, but we were interested in figuring out how well they actually work. And one central question was actually, how do we measure this? Because we typically don't have ground truths. We don't have access to the shape of the lenses in the camera systems. But what we can measure are biases and reprojection errors. So if you calibrate a camera, you typically compute correspondences between pixels in the image and 3D points in the scene, and then you can project the 3D points into the image and see how close they project to the 2D measurements. So here's like a conceptual example. Black are reprojections of points, and gray are the original 2D points. And ideally, you would like to see some random pattern versus where if you have something like this, where you have a region where all projections are offset by some same amount, then this indicates that your camera calibration model can't actually describe that region well. So let's look at some visualizations. We are visualizing reprojection error directions. So you see this on the right. If the point is projected, if this is the original 2D measurement, if the point is projected somewhere up here, you get a green color, here you get a pinkish color. And what you would like to see is something like this, a completely random pattern. There should be no patterns in this reprojection error directions. What you see in practice is something more like this. So this is like a typical camera model with 12 parameters, and you see that there are clear patterns in these reprojection error directions. So we reduce this to the assumption that 12 or 10 or whatever parameters might not be enough, and move to so-called generic camera models. So the idea is that for each pixel, you can have a complete array that's completely independent of all other pixels. You don't have a single parametric function. That's typically a lot of parameters that you need to fit if you have an individual ray per pixel. So you typically make some smoothness assumptions that these rays vary smoothly over the image. You can also do the same thing with non-central cameras, meaning that there's not a single center of projection, but you could in theory have a center of projection for each pixel. And for both models, we get a number of parameters for the calibration models that are roughly in the number of pixels. We built a calibration pipeline that starts with data capture. For this, we designed a calibration pattern, which has this Siemens star-like design. We first do feature extraction, so we try to find the center of the pattern, and then we refine it by exploiting the fact that this is actually a symmetric pattern. so we can use this to refine the detections. We initialize using an existing model, and because we don't want to store a pixel array per pixel, we rather define a set of control points, and for a given pixel, can then obtain the corresponding ray by B-spline interpolation of the rays stored for the control points. And then in the end, we optimize over the full calibration pattern, calibration parameters. Here are some examples. So this is the calibration that we get for a color sensor of an RGBD camera. This is a standard thin prism model with 12 parameters. We clearly see a bias pattern. This is OpenCV's camera model, which coincidentally also has 12 parameters. We again see some patterns. But if we go to generic models with many more parameters, so this is roughly 5,000 parameters, this is 10,000 parameters, this is 25,000 parameters, we see that we actually get bias-free calibrations. Here's another example for a smartphone camera where we can see that if we go to a generic model, we can remove most of the bias patterns. There are still some patterns here that you can see, but those are more global and not local patterns. Okay, so these generic models help us to avoid biases and calibrations.
So Torsten,
yeah.
2 minutes maximum.
Yes, I'll be done in a minute. But is the effect really measurable? So here's some visualization of reprojection errors between like a standard and a central model, and it's a maximum like 0.2 pixels, which begs the question whether this makes a difference in practice. And it turns out it does. If we run a reconstruction algorithm that reconstructs the trajectory, then this is what we get with a generic model, this is what we get with a parametric model, and we see that there is a significant difference in the endpoints. They start from the same point, and then they diverge. And this is just explained by using different camera models. Obviously, it depends on how well the generic model, the parametric model fits the camera. It can be less drift. But overall, what we saw is that the correct model makes a significant difference. And we ran a lot of experiments, and we have code available if you want to try it out. Thank you very much.
Torsten, I thank you. So questions, please.
Just if I may, Torsten, a curiosity question. I suppose that the drift effect, it's more prominent in the scenarios where the feature points are not spread uniformly over the whole image, right? Because there are some patterns in the parametric model, but if you consider the image as a whole, don't they clear themselves out by themselves?
No, that doesn't seem to be the case, that they clear themselves out, because you can't actually correct the standard bundle adjustment does not correct for those bias patterns. It gets worse if you have only few correspondences, or correspondences only in certain regions. But even if you have them over the whole image, I would expect that it's not. I mean, having more correspondences will help, but it will still get you to a different local minimum.
Okay, thank you.
Okay, thank you. I'm happy that, even at Faculty of Electrical Engineering, Tomáš Svoboda, who asked the question, is the head of the Department of Cybernetics at FEL. Okay, thank you. The next speaker is Pavel Kresek. Pavel, are you ready? Switch on.
Yes, I'm ready. I'm switching now. Do you see my presentation?
We don't see your screen yet. We see PK on the screen.
Maybe that screen one. Now, you see it?
Yes, we see it.
Thank you very much. I would like to present the article, the journal article, which is focused on the detection of radioactive pieces in some waste. And it was prepared in frame of the project Radio Rosso. The data were captured in 2018, and the article was published last year, 2020. The article and the project was prepared or written in cooperation with SURO, it's National Radiation Protection Institute. What's the motivation of the measurement? We have some radioactive waste material which called magnox. It's a rest of used fuel rods. It's shown on the image on the right side. The waste consists of the very rare fragments of the fuel with very high activity, then with a few small parts, typically stainless steel parts with relatively high activity, and rest of the material with, in that case, relatively low activity. And there could be some water because it's stored in the water, and some other construction material, but both with the relatively low activity. The main idea was to take out the high active parts, store that active parts in another way, because it's very small volume of the waste, and it's relatively expensive storage. But most of the material could be stored more easily and really more cheaper. We used other methods to detect the parts because, for example, the stainless parts are known, but in that case, we used the CZT radiation detector to detect the places of activity, and then the parts was detected by another vision systems. Okay, what we have? We have robot Bottoman. On the gripper was mounted the CZT detector. It's semiconductor detector which works in the normal temperature. Inside it is the crystal, which the size is 1 cubic centimeter. And it's relatively expensive, but cheaper than standard detectors for that task. And we have the waste. You can see on the right side of the robot. In the thin layer, it means a few centimeters of the material. And we move with the sensor above the material. In the article is mentioned 2 experiments in 1 centimeter and 10 centimeters above the surface of the material. But we try another positions and so on. It's problem we can not to use the real material. We have some artificial waste, you can see there, and for the localization we use the artificial radioactive sources. One was the cesium, one was the cobalt. Okay, that corresponds with the material which should be in the original waste. Okay, how we do that? We move the robot hand above the surface of the material. Some sample trajectory is shown on the image on the right side. And on the second image, there is the detection rates. We detect number of the, what it calls shots, number of the particles, which was counted each tenth of second. For the article is focused on the important question for practical use. One is if we are able to detect the pieces with the sim activity, and the second one, how then should be the movement. In the article, there is present the Monte Carlo simulation when the minimal detectable activities is looking for, and the FEP full energy peak detection efficiency is tested too. The parameters was computed for different type of shielding material. We suppose that the important or interesting parts are shielded by the standard material, by the water, and maybe by the some parts of the concrete or some parts of the construction material. And finally, there was done the comparison between of simulation and semi-analytic estimation of the activities in selected positions.
Pavle, you have only less than 2 minutes.
That's okay. Last slide and video. Okay, there is many tables and graphs in the article, but for us, or for technically for us, the most interesting is that the cobalt particles could be detected when they are shielded by 10 centimeters of steel or 40 centimeters of water, and cesium particles could be detected in 50 centimeters of water. It's more than we supposed in our test condition or in the conditions of the sorting system. In the images, you can see the data captured with for the test with the two sources of the radiation. And finally, I show you the video, which shows the whole process. I prepare it. If yeah, that's okay. And now I hope you see the video.
We see the video and we can open the questions. Okay, questions to Pavel.
Oh, I can tell that it was a very interesting multidisciplinary cooperation with the people of our robotic group and with the people of Suro, which are interesting and interested in the radiations. And we learned many more about that physical of radiation things.
Someone has raised a hand and asking a question by raising hand.
Yeah, I have a question, if I may. And the Magnox fuel, it's the fuel from British reactors. They are all shut down, and the fuel is used for extracting plutonium for the British military program, namely for the bombs. So my question goes, it's very interesting, but who's funding the research?
So Václav Hlaváč, this was funded by European Commission, and you are right, the waste was from Sellafield site in Britain. Exactly that. They have vessels which are about 20 meters deep, 6 meters in diameter, which are full of mixed waste, which they need to reprocess. Okay, so this was a partial thing, and there was a company which is involved in doing the job, part of the consortium of the project. Is it enough?
That's excellent, thank you.
Okay, thank you. So, Pavle, I thank you. We move on because it's right time. Miroslav Kulich. So, Pavle, switch off your screen.
I try to do that, okay.
And Mirek Kulich.
I
We see your screen, Mirku. Go ahead. We even see the impact factor.
Okay, I hope you can see my screen.
The sound is not very good. Can you come closer to the microphone?
I am close enough, but maybe I'm in a small room, which makes the sound different. I will try to open my window, which can make it better. Okay, so is it better now?
It's much better.
Yes, much better.
So
like in Windows programs, you know, closing windows, opening windows help.
Yeah. So I would like to speak about the problem of searching for a static object by a team of several robots. We define this problem as traveling deliverance problem and solve it by a combination of meta-heuristic called generalized random search procedure and variable neighborhood descent. We published this research in the International Transaction in Operational Research Journal, which is one of the best journals in the area of operational research. To introduce the problem, I will use the similarity with well-known traveling salesman problem. So assume we have a water supply company and it wants to bill its customers. It means that some auditor of the company has to visit all the customers, read their water meters, and then can create bills. Of course, the auditor wants to make the visits efficient, so he tries to minimize the time he returns back to the company. This problem can be defined on a undirected graph. So we have vehicle vertices, edges. Each edge has associated some cost needed to travel through it, and also we have some starting location of the auditor. So as I said, the objective function, which is to be minimized, is simply the time or the length of the trajectory of the shortest Hamiltonian cycle. The traveling deliverance problem, on the other side, can be also applied in, let's say, water supply company scenario. In this situation, assume the case that the network of the company is broken at several places. So we have some cracked water pipes, and we want to repair all of them. And we know their positions. And in this case, we would like to minimize the amount of spilled water. So this amount of spilled water related to a single cracked pipe is somehow inconsistent with the time it was repaired. So in this time, we would like to optimize some different function. Here you can see that the function contains two sums instead of one sum, which is the case of the traveling salesman problem. Moreover, we also can assume the problem as finding. Sorry, somebody closed my door. We can also assume this problem as the problem of finding cracked water pipe from some limited set of possibilities. Here you can see that the objective function is almost the same. We just compute the average time some place is visited. So this problem is called traveling deliverance problem, and we address its multi-vehicle variant. So we have several, let's say, repairmen which coordinate their actions. This problem, the single variant and also multi-vehicle variant, is known to be NP-hard, and it's known combinatorial optimization problem for which many optimal solutions exist, which are slow. On the other hand, there are also approaches which produce suboptimal solutions, and on the other hand, they are well scalable. Our approach is based on a greedy randomized adaptive search procedure, which is meta-heuristic, and it follows an iterative framework. So to demonstrate its function, please look at the image. Here you can see the solution space, and for each solution, we have some value of objective function, and the goal is to find the global optimum. The graph heuristic starts with initial construction of some solution, and then the solution is sequentially improved by performing several so-called local searches. The local search is performed in the solution space by generating neighbors of the current solution using some operator. For example, we can exchange two nodes in the current road, or move one node from one route to another route, and so on. So after exploring the neighborhood of a single solution, we can choose the best one and assume it as a start point for the next iteration. And this way,
1 minute only left, please.
1 minute?
Yes.
Okay, so this way we can go into local minimum. Of course, as it's local minimum, we have to repeat this process several times, and finally we can get some optimal. Our contribution to the problem is that we introduced novel clustering heuristics for initial solution generation. We also designed a set of operators for different neighborhoods. We evaluated them, and also compared our approach with current approaches, and we can conclude that our approach is 50 to 90 times faster than the solutions which provide almost optimal solutions, and the quality of our solution is also high. Its deviation from the optimum is less than 2%, and we also extended our approach to the real robotics scenario and deployed the algorithm to real robots. So that's all from my side, and thank you for your attention, and we'll be happy to answer your questions.
Okay, so one question, short question, please. If not, I would ask Libor Přeučil to take over and deliver his presentation. Mirko, can you switch off your screen or stop presenting? Thank you. Libore,
So,
I see you. I don't see your screen.
I'm trying to share. Okay, this one. So
yes, we can see your screen. It's okay.
Now, so I'll just present. Oops. Come on.
You can
still see the screen?
Yes, now it's excellent.
Right. Okay, thank you. Okay, so hello everyone. So basically, I should present our advances in visual face recognition. Stream we are heading in the lab. So basically, what I'm going to talk about relates to the here cited journal paper, which was published last year in Robotics and Automation System, Autonomous System, and it's basically a kind of follow-up of the previous work, which was an oral at ECMR, which was organized in-house in the year before. So we are trying to keep this stream to come up to reasonable results. So this was a relatively nice success to publish in the journal, and basically the essence of the work is to follow up and further develop the visual face recognition systems, which seems to be a good way to go for robot navigation or mobile stuff, mobile device navigation in general in environments which are hard to describe. So with high level of uncertainty, which do vary over time with lighting conditions where the people are present around. So nothing can be described precise way. So basically this time we just followed up on the previous, and we show in this article that we succeeded to substantially improve the performance and precision of our previous solution. Basically the whole work is based on more or less standard image retrieval process, which comprises two-stage configuration. One is where we just search for closest candidates in an image database. So kind of image search. And the other one refines, let's say, the decision from the previous step by a geometric verification. Here we are coming up in the article also with a novel things which improve the geometric verification process and improve the performance very much. The whole thing, good reason to keep on this track is that the whole approach is very simple and remarkably robust to viewpoint conditions and to changes of lighting and all other things. So it can handle easily the uncertainty. Moreover, what we did in this work, which was really strongly experimental, so we did an extensive optimization of parameters and compared the whole solution to other existing approaches and public data sets. Basically, the motivation is the following. Lots of you should know. The overall thing is that we need to retrieve similar or best the same images. So make kind of query into image database of places, trying to realize where we are or where the robot is. The challenges here are all kinds of variations, like viewpoint change, day, night, weather, seasonal, etc., and of course dynamics in the environment. So presence of people, cars, and you can just imagine the environments. Applications are, for our case, rough localization, so a kidnappable problem, loop closure to recognize the place where we have been before, and of course teach and repeat applications, you know, from the experiments in our lab probably. So this is the let's say the structure we are using, relying on. So we have two kinds of databases: the spatial imaging database, which comprises the structure of the scene, and the image filtering database, which comprises the look of the scene. And we do offline database creation. So basically, so far we rely on pre-learned neural nets, and the online recognition process goes in real time, comparing those two and fusing those two decision-making steps into final decision. Basically, this is what I already mentioned in the beginning. This is just the list of the major methods we compared our approach to, and the bullets which show let's say what we did in this time. And basically we are using the Kitty data sets and similar ones. In this case, you have seen in the previous slide the types of scenes we are working with. And of course, we this time also extended by all data sets created based on Google Maps and Northland data sets, exhibiting something like 8,000 images. These are the results, and this is the crucial thing to show that if you just look on the bar graphs, the right 5 bars show up the results we came to. So we are proud about the last violet one, which says that we are, well, our decision or our recognition is correct in 98.8%. So which is just a wonderful result. And this has been achieved just in the last steps by the improvement the scene from 90% to 98, nearly 99% of reliability of correct recognition. So For further details on that, I would recommend you to go into the original paper at the journal, because there are much more details on that. What we did achieve, what we feel we achieved, is that what I already mentioned. So this concept seems to be really reliable, really usable, even for real-time real-world applications. And we are, with the data sets which we run the approach on, achieving nearly perfect recognition results, which is wonderful. So the outcome now is that we have improved the geometric verification queries, candidate image selection. We included spatial temporal correlation between frames, so the evolution of the environment we work in, and that's the core what we achieved so far, and where we also see the future challenges, which is our fear that if we grow in size of the database we work with, or we will go for images with larger viewpoint changes, it may be worse, the result. So that's the scientific question, whether the trainable architecture which are necessary to be used for these cases will exhibit lower precision or not, or how to adjust this. So that's the main challenge. And the last but not the least thing is just a short video. You should probably, you might have seen before.
We have only 40 seconds, Libore.
It's 40 seconds video. Okay, so this demonstrates just, let's say, artificial intelligence, artificial environments. So it just proves somehow simple way it can be used in production environments, the final solutions. So the teach and repeat navigation, or we can operate the mobile things also outdoors in environments like this. So this is just a simple demonstration from the campus area.
Libore, please stop. I like to hand over in time, which is 10 seconds before the stop. Okay. So, Mr. Chairman, Zdeněk Hanzálek, our team is finished in time. Thank you that you listened to us. Thank you very much.
Okay, thank you, Vašek.
Libore, could you stop sharing your video that the others can?
Oh, sorry, I have to.
Okay.
Excuse me.
And the next presentation comes from the Industrial Production and Automation, and it should be Tomáš Vyhlídal, Zbyněk Šika, and so on.
Hello, everybody. My name is Peter Kolar. I'm Deputy Head of the Department of Industrial Production and Automation, and I would like to start our blog with a very brief introduction of our department. As you can see, my presentation here, I would like to say that our department is organized within four research groups. But due to running projects, we are working as two teams. We are using these numbers, so that's not important now. What is more important, the first team is responsible for the laboratory of robotics and manufacturing technology. You know it maybe as so-called lower testbed, which is the laboratory of production machines in the basement of the CIIRC, and we are focused in that laboratory and robotics and automation, industrial and collaborative robots, then industrial communication and production data processes, and production processes fundamentals, mainly research processes, machining processes, additive manufacturing processes, and digital twins of production machines and processes. Another team works in close collaboration with Department of Instrumentation of Control Engineering at Faculty of Mechanical Engineering at CTU, and these colleagues are focused on control of system with time delay, and within the projects that are running on CIIRC, they collaborate mainly within National Center of Cybernetics and Artificial Intelligence, and also Grant Agency of Czech Republic grants. So that was a very brief introduction of our department, and now I would like to invite Professor Tomáš Vyhlídal with first presentation from our blog, which is about two-dimensional delayed resonator for entire vibration absorption. So I will stop sharing my screen and I would like to ask Tomáš for his presentation.
So in my presentation, I will look at the results of our recently published paper, a two-dimensional delayed resonator for entire vibration absorption. The paper has been written by me and my colleagues, Professor Zbigněk Šika and Dr. Zbigněk Neuser from the Faculty of Mechanical Engineering. These results have been achieved within a CIIRC Foundation project, which has been completed, or which was completed in 2019, and the project was evaluated as excellent project by the CIIRC Foundation panel of Mechanical Engineering and also by the Presidium. Currently, we have started a new project by CIIRC Foundation in which we will continue in the research. So let me make an overview of the delayed resonator concept. So this is a method to design an ideal vibration absorber, and the idea was introduced by Professor Hlaváč in '90s. They have done a lot of work on that, and about 8 years ago, we have also started to work on the topic, and we had a couple of papers also with Professor Hlaváč. So it was before the project started. Let me very briefly outline the idea or what is behind the delayed resonator concept for one-dimensional vibration absorption. So here we have the scheme. So assume that we have a platform which is being excited by a periodic force. The amplitude of the force is not known. We only know the frequency. And above that, we have an absorber, and the absorber is active. So we have next to the damper and the spring, we have an actuator by which we try to achieve ideal vibration absorption. So the objective is to stop this platform vibrating while all the energy which is brought by the periodic force is absorbed to the motion of the active absorber. So in one-dimensional case here, the synthesis is relatively easy. It is based on a pure pole placement method. So at the end, we can see something like this. So this comes from the measurements. So after the active absorber is switched on, so all the vibrations are absorbed. So the motion of the absorber is increased, and the platform, on the other hand, is silenced. So let me show this on the video. So this is the platform.
No caps SMT.
Can you see it? So the platform is being excited by the voice coil linear motor, and here we have the absorber. I also forget to mention that the very important point, that the control synthesis. Now you see that the absorption is working. So the platform was silenced, and all the energy was passed to the active absorber. I forgot to mention the key advantage of the absorber, and that is the synthesis is not. For the synthesis, we don't need the parameters of the platform. So everything what we need to have is the parameters of the absorber. And also the sensor is placed on the absorber, so it can be mounted everywhere, the platform, and it all should be working. So the main objective of the project was to extend the idea of this delayed resonator from 1D to 2D case. Yeah? So in 2 dimensions, or suppressing vibration in 2 dimensions, it's much more difficult because instead of 1 triple of the damper, spring, and actuator, we have 3 triples, and they need to be somehow coordinated. And also, we assume that the platform can move into the space, and this is the excitation force acting on the platform in some arbitrary direction. So first main results which you can find in the paper is given in the proposition 1, and it derives the parameters for achieving so-called ideal 2D absorber. Yeah, so you see here we have the matrix of the mass, matrix of stiffnesses, which is quite complicated for the considered configuration of the actuation, and you can also see that not only the stiffness of the springs is important, but also we have some restrictions on the dimensions and mass and the moment of inertia. So achieving or fulfilling these inequalities or equalities, we obtain the ideal unifrequency absorber. You can also see that the damping is missing here. And the main result is given in the theorem 1, which says that when we place such an ideal absorber on a platform, so it will fully absorb the vibration. The proof is based on singular value decomposition and on studying the behavior of singular values of the multiple input, multiple output systems. So the synthesis is much more difficult in this MIMO case because we cannot look only at the frequency, but we need to observe the singular values. So in the subsequent step, we turn the physical absorber to an ideal absorber by applying the time delay control feedback. So this is actually identical to the one-dimensional case. So we use the same type of algorithms, but we have 3 actuations, and everything is considerably more difficult. In the paper, we show or we demonstrate that it works by simulations and by analysis. So the simulation results are here. So you see that also after we switch the absorber feedback on, so which has happened in time 10 seconds. The platform vibration was silenced. We also see here the behavior of the singular values with respect to the frequency. The frequency to be suppressed here was 12 radians per second, and we see that the absorber, the active absorber, has a resonance frequency here, which are projected to the anti-resonance of the platform. In the spectral design that it works is demonstrated by the fact that we place a triple root at the target frequency. So future steps are to perform the experimental verification, which we have already built the setup, which mirrors the structure of the 1D case. So far, we have not tested whether it works on a platform, but you see that we already have something, or at least some video. Another future step is to move forward this idea to 3-dimensional case. So in that, for that we will need not only 3 actuators, but 6. And also dampers and springs. So this is all from me. So if you have any questions.
Thank you, Tomáš. We have time for 2 questions, maybe. Are there questions, please, from auditorium? It seems there are no questions from auditorium, so paper
yes,
available. So thank you, Tomáš, for this presentation.
Yeah, so this is still classical control theory. I think we are the only ones with Vladimír Kučera who is doing this at CIIRC. Yeah, so, but it's also exciting, like the other topics, at least for us. Yeah, so
Okay, yeah, definitely.
Josef Hlaváč, is this also exciting for us?
Okay, thank you.
Okay, thank you for these comments. And now I would like to invite our colleagues Michal Kuchař and Adam Pajdla, and they will present results of National Center of Competence, Cybernetics and Artificial Intelligence, called Hydroelectric Powerplant Simulator. So, dear colleagues, please share your screen. Floor is yours.
Okay.
Yes, we can see the screen. Perfect.
So, hi everyone. My name is Michal Kuchař, and me and my colleague Adam Pajdla are going to present you our work at a project called Hydroelectric Powerplant Simulator. We worked under supervision of Tomáš Vyhlídal and Jaromír Fischer. In the first part, we will show you a mathematical model which we used, and then we will show you our web-based simulator developed in a Python programming language. And finally, the implementation in industrial software called Pertinax, which is developed by that company. Let's look at the project timeline. Our work started in 2019 when our group with Professor Zítek made up the model. At the start of 2020, it was desirable to visually present the model and make a validation on real data. So for the model visualization and validation, we decided to develop a web-based application. After validation by that company, we made a C++ class representing turbine model. That company made an interface for implementing the class into their industrial software. Nowadays, the model is validated by that company, and one of the future goals is to implement a model which takes into account a water hammer effect and leads to a time-delayed system. We are also working on an automatic identification of the parameters. Here, we can see a simplified scheme of a hydroelectric power plant, where we can see that the water goes from the reservoir through a penstock and through wicket gate to the turbine blades. The turbine is controlled by wicket gate position, which distributes the water to turbine blades. We can estimate some parameters from the power plant parameters. So, for example, mechanical inertia time constant can be estimated from the moment of inertia, the nominal angular velocity of the turbine, and also the nominal power of the turbine. The other time constant, the water time constant, is dependent on a flow, gravity, water level, and dimensions of the penstock, where these are the partial length and cross sections of the penstock. And finally, you can see the model which we used, which is in the relative deviation form. It means that these magnitudes are in relative form. The phi is a relative speed, psi is a relative wicket gate position, mi is a relative power. When the turbine is not connected to the power grid, we can express the speed from this first equation, and the wicket gate position and power are input to this system. But after connecting to the grid, we can consider the delta phi, the speed is, or the change of the speed is 0, and we can express the power which is controlled by the wicket gate position. You can notice that the model has quite low number of parameters, and here you can notice that it is a non-minimum phase system, where this constant is that water time constant from the penstock parameters, which has the influence of that non-minimum phase. Now the numerical implementation, we solved it in the state space representation using Hoynes method, which we used because the method is easy to implement and sufficient enough for our purpose. It is also necessary to shift operating points because the regimes are switching. First regime is a speed ramp, where the speed needs to reach the nominal speed value, and this regime starts with the operating point where are all zeros. But when we want to connect to the power grid, after reaching the nominal speed, we have to shift the operating points to the wicket gate position at that switching time, and shift the speed, the nominal value of the speed. So it's a relative form, so it is 1. And the last regime is the power grid disconnection, and it is necessary to shift all the operating points at that time, at that switching time, when the disconnection occurs. Now I will. It's time for Adam Pajdla.
Okay, thank you. So let me briefly introduce implemented Powerplant simulator. We have chosen Python 3 as a programming language because it is suitable for rapid prototyping, and also because several great open source libraries we used in the project are easily accessible. The web application is built on Flask and internally uses object role modeling concept for SQL database access. And of course, we used NumPy for numerical computations and Plotly library for visualizations. Also, this application runs in Docker, so it's completely platform independent. On the following slides, I will try to demonstrate what the implemented web application looks like and what it is capable of. Here you can see the file upload screen. So each user has its own workspace. For safety reasons, of course, you have to log in and access all the functionalities. And here it's possible to upload measured data for comparison with own parameterized models. via simple form, you can create multiple parameterizations of water turbine model. You can test them and compare them to measured data you uploaded before. On the figure on the right side, you can see the comparison of model response of rotation speed, the wicket gate position, and measured response. Let's go next slide. On the figure on the right side, you can see power control and power control mode of model. That means that turbine is connected to grid. And please also note that the user can define gains as a set of points, which effectively makes it possible to form even a non-linear model. And here, the last slide for model parameterization. You can see simulation, how the model behaves when the turbine is suddenly disconnected from the grid. On this slide, you can see simulation of regulation. In the left panel, user can set up various parameters for regulation. And on the right side, there is also visualization. Please also note the darker color of background represents that the water turbine is connected to grid. And here you can see, again, left panel, you can set up various PID regulator parameters and also some restrictions, for example, on the maximal wicket gate position derivation and a restriction on set point. Do not get confused by multiple parameters. It is just a convention of our industrial partner, ZAT. It's just a regular PID regulator. And the last slide for web application. On the left side, you can see 3 different power levels and its duration. And on the right side, you can see rotation speed. Red line is set point and blue is the real rotation speed. And again, darker background means it's a water turbine, it's connected to grid. Also, we implemented C++ header-only library for our industrial partner. And here I just, on this slide, just you can see the block scheme of water turbine regulation in Pertinax software tool, which is software tool our industrial partner uses. It's similar to MATLAB, but it has some advantages for them. And on the last slide, you can see Pertinax output. This is how output from their software looks like. You can see their regulation of power and also behavior of our model when it's disconnected from the grid. So that's all. We managed to design a model of water turbine. We also implemented application for model parameterization and PID design. And we also had to implement the model in C++ for our industrial partner. So thank you for your time. And now it's probably we have a few minutes for questions.
Thank you, colleagues, for your presentation. It was a nice example of applied research done together with industrial partner. So I would like to ask colleagues from auditorium if they have some question, please. You can ask now. Tomáš Vyhlídal, would you like to comment a little bit about other details of this project? Would you like to comment a little bit collaboration with ZAT company, because there is longer tradition of your group in collaboration with this company, if I'm right?
Mm-hmm. Yeah, maybe I would mention the main motivation. Yeah, so it's the motivation is behind, or the motivation is of this research is to establish some methods which will help the end user to tune or to pre-tune the parameters of the PID controllers before the system is implemented to the water power plant. We have tested, even though our model is relatively simple, it's balanced model. It can fit relatively well the measured data. So we used we have measured. I hope I can say that we had data from Lipno and also from Gabčíkovo. And in both cases, we can parameterize the model there to fit the real data. From a theoretical point of view, we are interested in the models with with the power plants with long penstock, because in that case it becomes a system with distributed parameters, and we can model it by time delay system, and it's also by a special class of time delay system, so-called neutral systems, which are interested by the fact that they can have infinitely many unstable modes if the control is not tuned well. So this applied research also give us some potential for doing theoretical research. Currently, we plan to submit, or we are close to submitting a conference paper on this topic, the time delay system.
Okay.
And maybe let me also mention the last thing. So currently another topic is to propose algorithms for automating the parameter assessment from measured data. So this is a topic Michal Kuchař is working at the moment.
Okay, thank you for providing us these details. Thank you, colleagues, for nice presentation. And last presentation of our work will be done by me. It's also about result of applied research from the project of National Center of Components, Cybernetics and Artificial Intelligence, and we selected results called laser device integrated into a machine tool. The project is focused on toolpath generation and process control for laser powder additive manufacturing. As you can see, there is application head, there is a fiber laser and powder. The head is moved by robot, and there is the part which is produced using additive manufacturing. In collaboration with Laserterm company, we were responsible for preparation of algorithm for toolpath planning and concurrently for control of the, not control, but for planning of parameters of the process. I would like to start with this introduction. This is, for example, a volume of material that we would like to produce, and this volume is can be built from this particular parts of material. There are various strategies. You can start from outside and go to the inner part, or you can start in the middle and go to the outer part of the contour. Every time for these various strategies, it is necessary to have various setting of process parameters. Process parameters means a combination of the power of the laser unit, powder flow, and then moving speed and orientation of the application head. Powder flow is estimated as a constant. We don't control it normally, but speed of the head movement and orientation of the application head and the power of the laser source, these are three parameters that are controlled and set. During initial tests within our project, we used this this approach for automatic feedback on process setting. We set a combination of these three orange highlighted parameters. Then we generated two paths and built the requested 3D part. Then we scanned the part and compared the ideal volume from CAD and the real volume taken by scanner. From comparing of both volumes, we noticed if the settings was successful and if we have enough deposit material or if some volume is missing. So that was evaluation of the process planning module. And then we were also involved in tool path generation using standard CAM environment. We worked on Siemens NX CAM, which is quite common industrial standard. And for this CAM software, we prepared functions that are able to generate tool paths. You can see here various strategies for tool paths of movement of the application head along the basic or fundamental volume. So you can see here, for example, cylinder, and on the cylinder we have generated tool path. This toolpath generation module is connected together with another module that was prepared by us in collaboration with the company. And this is the process module where are results from the previous process experiments and recommended settings for the whole laser process. So combination of these two modules, or using these two modules in CAM software, it is possible to generate NC code for application head movement and also for control of the laser power on the processing head. So here you can see example on a very simple part on cylindrical deposition of the material. The result of the project was the functional sample of the laser device functionally integrated with the robot. So this laser device is integrated together with the robot, and within the whole process planning workflow, we prepared all necessary functions for CAM software. Using combination of toolpath planning and also process information, it is possible also to produce more complicated geometries, like in this case, this is a screw profile for a pressing machine. I have to say that this research continues now in two ways. In second part of the National Center of Competence, we continue on topic of toolpath planning for machining of compliant parts using robot, and another stream more related to process identification and optimization will be now part of on a use case in RECAPE project. That's all from my side. Thank you for your attention. Are there some questions from auditorium? If not, yes.
I would have a question. This you say you measure the generated material. You measure it online, or it's just during the like a training, or how to call it?
No. I have to say that we used quite a primitive approach because we had offline post-process scanning of the volume, and then also offline comparison of all volumes. This was sufficient for generation and evaluation of the initial setting of the process parameter. to do it more automatically, and also to use maybe some algorithm of artificial intelligence for identification of the optimal parameters for various geometries. That's the topic for future research. Thank you for these questions. Are there some other questions, maybe also to previous presentations from Tomáš Vyhlídal?
Yeah, I have one question to Tomáš Vyhlídal. This is Baran Alikoč speaking. Hello, Tomáš. I would like to ask why not to use two 1D absorbers handling vibrations in each dimensions. Is it because of some mechanical restrictions, or it has some advantageous characteristics to suppress vibrations?
Thank you, Baran. It's an interesting question. Of course, it should be possible. I'm not sure if two will be enough. I think we would need three, because we have three degrees of freedom. We will need to perform analysis. Yeah, of course, we have thought of this too. And we also look at literature. Yes, so what they say on the advantages of multidimensional absorbers compared to single-dimensional multiple absorbers. And yeah, in literature they say that the multidimensional absorber has a number of advantages, but we have not done the analysis ourselves. Yeah, so this is maybe the main advantage is that you have everything together. Yeah, that you have only one absorber.
Oh,
so it may be easier to place it. And concerning the performance, whether it works, sorry. So we believe that it works better. Okay, so we can discuss it
in person. Okay. Thanks.
Baran, thank you for your question, and I would like to ask you to discuss it maybe with Tomáš in person, more in detail. Dear colleagues, thank you for your attention for this presentation of the Industrial Production and Automation Department. And now I would like to ask Professor Lenka Hlhocká for steering the presentation of her department. Thank you.
Thank you very much. Good afternoon, ladies and gentlemen. Sorry, I don't know what's happened with the presentation. There is completely different presentation that I wanted to share, so I have to find the right one. Very briefly, my department is focused on research in cognitive systems and neuroscience, and also connected topics. Last year we were quite successful with journal publications. Here you can see the list, and also with conferences where we presented our results. Again, there were different conferences, but all of them listed on the Web of Science. And last but not least, we also organized one conference. Originally, it was planned as standard physical conference, but due to the COVID-19 pandemic, we had to organize it finally as a virtual event. Finally, it was very successful, and the proceedings is available in open access regime, so everybody can look at it and read, I would say, very interesting paper there. That's all from my side, and now I would like to hand over to Václav Křemen, who will present his research results. Václav Křemen is currently our ambassador at Mayo Clinic at Rochester, USA. So Václav, please, the floor is yours.
Good afternoon, everybody. Let me check if I can see my
presentation here. All right. Can you confirm you see it properly?
Yes, it's perfect.
Okay, great. Okay, let's do the pen here. Yep, so instead of one paper, I'd like to just show and share with you really intriguing research that we do here at Mayo Clinic with the help of some researchers from CIIRC University as well, and some algorithmical machine learning stuff. But I just think the whole line of and direction of work might be interesting to everybody, just to see if they can somehow maybe talk to me later or cooperate with the algorithms that CIIRC researchers does. I really like these symposia. I was watching yesterday and today, and it's a great groups of people. So I'm gonna be talking about brain implants that might be using machine learning as a co-processors to control the chronic brain electrical stimulation. What's the motivation here? We mainly work with people with epilepsy, so it's very specific use case of using implantables. There are other diseases where it is also used, like Parkinson's or tremors. I will show the epilepsy case here today, where about 1/3 of people with epilepsy, they are not treatable by medication or surgery. So they are either left behind, or they can have brain implant, the electrical stimulation device that stimulates their brain and modulates the brain activity to either stop or prevent seizures from happening. So for them, the brain stimulation is the option here. But I have to say, compared to what we saw yesterday here, this excellent amount of work with big data in industry, the neural devices and the whole field is rather, I would say, conservative. So if you look into the hardware capabilities of the devices, they are very limited. It's very hard to get accurate seizure diaries. So if patient reports the seizures, they are not aware of them, and the devices are not able to provide us with the accurate diaries as well. So even the biomarker, the main biomarker, seizure counts or seizure frequency here, is basically biased by a big error. The patients, even though they have implants, they are rarely seizure-free now, still with the capabilities of devices. So finding the better therapies, stimulation therapies, is really important. And there is a big question how we can control better the stimulation, maybe adaptively, because the brain, of course, adapts brains. It's a great invention of the nature and genetics, and adapts to the condition and in different scales. So how we can cope with this limited analytics, not optimal electrical stimulation therapies. Dr. Worrell, who is my PI at Mayo Clinic, was thinking about the next generation epilepsy management platform, which could have integrate the implants that are able to stream and send some data with distributed computing that may be using some more effective algorithms that will inform the stimulation back in the device and find the optimal adaptive stimulation for the patients. So in this big study, which was a multi-center study, private-public partnership study with companies. The Medtronic company delivered new investigation devices that were able to telemetry the data from the devices, which is very unique still today. And we wanted to show that we are able to even detect and catalog the seizures properly, that we can do some responsive adaptive stimulation. We had a canine models implanted, dogs implanted with devices, I will show you later. And we wanted to see if we can forecast seizures to stimulate better, even before the seizure happens to prevent seizures from happening. And then finally, we wanted to get the FDA approval here and start with the study in human subjects. So this is kind of a global picture of hardware, how it should look like. So either dogs first in the study or humans, they have implanted electrodes in deep brain structures, and the device basically sensing data and streaming it up to the cloud. Unfortunately, even the current device cannot stream it directly to the cloud, so they have to have some personal access device like tablet with the antenna, then streams the data up to the cloud. So this connection goes back and forth with safe U-band, which is about 400 megahertz, and this goes up to Bluetooth. And it was the same with dogs and human. And what we want to do on cloud is that we can collect some and catalog the data somehow a sophisticated way. So we wanted to see how the people sleep actually. You know, this is the 7-day sleep pattern automatically analyzed from one of the human data. We want to see some biomarkers like electrical discharges that those epileptic patients very often have. And of course, we want to see the seizure probability matrix and want to see if we are able to predict seizures. And even before that, we want to see if we are able to detect seizures. This is how the seizure looks like. This is kind of like normal brain activity, and then it attenuates a little bit with high frequency, low power, and then it goes up to big spiking and big discharges in the brain. And usually with our patients, which is temporal epilepsy, they are unconscious during the seizures. So that's kind of big picture what we wanted to do. And we designed a therapeutic system for this with the implanted device. So we would have patient on one side implanted with the device, streaming data up to the cloud. And then we would have physician having the same cloud and downloading the data and reviewing the data from the cloud. Something like that, where you have, this is the dog subjects here, where you see some basic data, then you see some longitudinal trends, like how patients are charging the battery of the device and so on. And then you can see some seizures here, real events, you can see some detections. And then we would also want to have some tools that we will be able to look at the data more carefully. So we could review spikes and seizures, different stimulation patterns, and so on. And we also want to do some smarter analysis. So here you see use of Certicon Cyber PSG tool for clustering the data. You see nice sleep cycles of dogs here going up and forth. This is like 1 day for the dog here. You see the spectrogram, the dog's going down to sleep, awake, sleep, maybe REM, sleep, REM, and then awakes here. So these kind of tools we building together, and we wanted to build a closed loop between the patient data, patient brain, to optimize the therapy, and between the physician that will be able to see the data and kick in some different settings for the patient if it's needed. What's behind the cloud? It's the magic actually. So the hardware is one piece, but the cloud that we build is the whole big infrastructure that we created in the lab. Of course, it has some storage here. It has some metadata servers, the database servers that gets a lot of metadata from the patients that can, for example, fill in the medication that they are taking, or they can do the questionnaires like mood scale questionnaires, or they can fill in how they slept last night and so on. They can fill in the seizures. And we also get a lot of metadata from the device, the settings of parameters, what is the amplitude of stimulation, and so on. So this is collected here, and we used some computational infrastructure in the lab, and we built a lot of machine learning tools. I'd say it's really like machine learning more than AI, or we can call it narrow AI. You all here are experts on AI, so it's nothing too much sophisticated, but it's a lot of new machine learning algorithms that we developed along the way for enterical epilepsy, form discharges, seizure detections, automated sleep staging from the brain data that we get from the patient, and seizure prediction. We finally implanted about 13 dog subjects, which we tested the device in, troubleshoot all the system, and de-risk the whole system. And then currently we have implanted 4 patients for human subjects in the study, and we are collecting data. One subject is giving us data more than 18 months right now, continuous 24/7 monitoring. So what's under hood regarding the algorithms? We did some deep learning LSTM models for seizure detection that we trained on a big data set of data from Neurovista human study, which was 11 subjects monitored intracranially over months. And we generalized the model, so we were able to use it on animals and then on our humans, and we confirmed and published the results from it. We also did the sleep classification model from intracranial data. This is under review right now. And then we built some convolutional neural network model, just the first stage of the model for seizure prediction. We are still developing this piece, so more will come later. And we had some feature engineering normal clustering methods, comparing it with autoencoders and deep clustering methods for explaining the various time scale adaptability of electrophysiological data in the brain on different conditions. Here's how it all looks when the physician looks at it. I put all figures together, but it's basically different screens from major characteristic values, how the physician can see how the patient's charging the device, how much data did we get, and so on. Where was the last seizure? So we see last seizure was 6 hours back, which is quite close. That's why it's red. Then we can see how patients marking the data and seizures. We can see the detector, how is detecting the seizures, and then we can see what are real detections. So you see some few false positive detections here, which is on purpose because we wanted to have it hypersensitive, just not to miss any seizure. And then you can see the raw EEG data with the seizure itself here. That's marked as gold standard with this yellow frame. And here is Certicon Cyber PSG tool that we used for analyzing some of the seizures. This is patient coming from anesthesia here. You see the change in spectral data and in raw EEG data power as well. So this was a big project that need to undergo all the scrutiny. Okay, all the scrutiny FDA. We got FDA ID approval and got implanted human subjects finally. We starting to do some discoveries with the data. We are observing the cycles of biomarkers and seizures and relations between those cycles. So we hope we can use it for seizure prediction, for example. We sharing and disseminating those tools. We are partners in big implantation devices group, which is called Open Mind. So all the tools are available. I just put in last 2 years publication where the CIIRC co-authors, either me or others, are here as well. It's all in peer-reviewed journals, and in other field that we are working on, we were lucky to get a US patent as well for the device that's measuring blood pressure waveform. This was a cooperation of academic and private sector, CIIRC Cocsus group of Professor Hocka, Certicon private company, Medtronic private company, and of course Mayo Clinic and other US clinics in game as well. So thanks much for attention. It was really quick, so I apologize. If anybody wants to follow up on that, you can contact me by email, of course.
Thank you very much, Václav. And there is time just for one short question, if there is any.
Can I have, this is Josef
Yes.
Šivic. Can I have a quick question? What kind of data scale are you talking about when you say you train convolutional network to predict seizures? How many kind of examples you've collected in the data set in order of magnitude? It's exciting. It's a very nice effort. Yeah, so we are collecting EEG data with sampling rate 500 Hertz or 250 over months and years now.
But I mean,
so,
how many positive examples? Like, are you getting like thousands of like seizures in your?
So the seizures that we collect, it's pretty rare event, and that's one of the pitfall of epilepsy monitoring. So patients usually have seizures few times a week, sometimes even a few times a month. So you have a very unbalanced data set for that.
Okay, thank you very much. Thank you very much. And now I would like to invite Lenka Vysloužilova, and she will present the project Vent Connect. Lenka, the floor is yours. Please switch on your microphone.
So once more, good afternoon. It's my pleasure to show you the project Vent Connect. It was our response to the coming autumn crisis in hospitals with COVID-19. And we do it with cooperation with the faculty or hospital in Vinohrady, and the team from Czech Technical University was from CIIRC, Faculty of Electrical Engineering and Biomedical Engineering. So some project objectives. So we start at October 2020, and there was some problems with very experienced doctors who could care for COVID-19 patients, which they predict will come. So they want some assistant in monitoring patients in the infect zone and communicate between doctors and between personnel. And of course, supervision means take some knowledge from one doctor to other, because there was many patients and very short doctors. So the project after half of a year is in different position. So now we talk about a long-term monitoring of patient vital functions, and we know now that there is big space to explore the effect of artificial lung ventilation on patients. It means COVID-19 show us that we don't know enough about this ventilation. So here is the first version of our system. Here I have mouse. So this is artificial lung. It's a balloon, and the ventilator works with this balloon, and you can see some pressure or some behavior of ventilation during the cycle. And here is the camera, which is look at the screen and send the data to some notebook or some device, and you can see the same screen on notebook as on the ventilator. This is the first version, as I said, and it brings one positive thing, because here you need the snowman suit. So and this is very infect environment, so it's better for doctor to sit in his office and look at the data. So here is some block diagram. We have many ventilator here, or the vital sign monitors, and there is 3 types of inputs. It can be without any input, means camera input, and or some video inputs. We use now the infrastructure of hospitals, so these cables are from hospitals, or we can use the Wi-Fi network, and we have there some router, and we can send the data to notebook inside the hospital, or we can transform it to some other place. And in current version, we save the data to our server, and we can show the records or long-term records to the doctor on their mobile phone or notebook. So in this project here there is very important to thinking about security and about anonymization of data, because the patients are in the worst state, means critical state, and it's very it's necessary to not show the data and the state of this patient to whole audience or to the whole world. So here is the photos of our device. Here is the device with Wi-Fi antenna, and this is version with classic Ethernet cable. Here is the video input, and yeah, it's very small box, which is close to the patient bedside and must be near the ventilator. Here are some results. What can the doctor see on his phone? So we call it magic mirror, because it's about fairy tale about Snow White. Please mirror, say me, how is the patient on or in the bed? So you can see that the screen is really similar, same as on the ventilator. this is ventilator, and here you can, you can see the monitor of vital function of many patients. Each line is one patient. This blue boxes anonymization. Normally, the doctor see there the name of the patient, but we can't transfer it to the web. So, our future plans, we prepare new version of software, and now we have 15 devices in the hospital of Vinohrady. We plan some extension to other hospitals, and we know that there is space for clinical research on the effect of artificial lung ventilation settings, means how the ventilator is set to the concrete patient and concrete situation of this patient. If the setting is better, we know that the prognosis of this patient is much more better. This can be different between life and death, so it's very important. And of course, we plan some commercialization of the system, and we see what the future brings. So here's some photos from the hospital. This is the first showing or presentation of the system to the doctors. Here is some pictures of how we prepare the installation. It means we must go to the infection zone. So our colleague must wear the snowman suit. So you can see he's white. And the last one is presentation of the system, where the doctors discuss the results on big canvas. It was very interesting. If you are in Calm and you see a small screen on a big canvas, it shows many things to them, and they discuss it very hard, every peak and every one point. So it was interesting for us. So here's our team, and here is the web page where you can find some more information about this project.
Thank you, Lenka, very much. And I see that there is no time now for questions, so maybe if we save some time at the end. And now I would like to ask Jindřich Adolf, last presenter from our group, to say something about movement analysis and telerehabilitation. Thank you. Go on.
Hello, everybody. Can you hear me and see my screen?
We see you, we hear you, but we don't see your screen.
Okay. And is it better now?
Not yet. We don't see the presentation, so hopefully it comes up.
And do you see this screen or not?
We see the screen. Yes, now. So you have to probably open it once more. Yes, now it's there.
Okay, so I will start. So my name is Jindřich Adolf. I'm PhD student, and Docent Lhocka is my supervisor. And today I will talk about remote physical therapy and single RGB camera motion sensing. So for introduction, I will say something about motivation. So we would like to create a system for rehabilitation and diagnosis in the home environment. And we would like to capture motion and tracking the body movements only by one RGB camera. So this idea is very easy, and the use at home is very easy, and it's a cheap solution. So I'm pretty sure you already know OpenPose because it's a very famous framework. So just to remind you, it's two-dimensional real-time multi-person key point detection. And in our case, we work only with 25 body key points, which is enough for our case. But you can also track the face key points and also hand key points. So maybe in future we will implement it, but for body movements, the body key points seems it's enough. So maybe the best is to show you how it works on this video. So I hope you can see it. You can see it. Yes. So I play it. So you can see it's me in the room, and you can see it's a lot of background and a lot of furniture in the room, and it's still the tracking of the body is working very well. So we can say we can use it in home environments, so we don't use any green screen or something like that. It doesn't matter if you wear a color I don't know, sweater or anything. And here on this graph, you can see it's the angle on the x-axis, it's time, and this is the angle of, for example, in this case, is angle of my spine. So I can see if I stand very, straight. So it's around 0 because it's right movement. In this case, you can see how my shoulders are moving, and I can see the angle between the shoulders and horizontal. So in case I would do the movements some wrong way, I can see this in the graph in the angle. So here in this screen in this video, you can see some easy statistical information, and this output we've created for physiotherapists, because we work with physiotherapists, and for them it's very it's not easy to read some data and tables. So in this case, in this video representation, they can see the person, they can see the body key points, and they can see the output, and they can easily see what's going on. So we can track the angles, but also relative distances. So for example, here you can see the relative distances between shoulder and ankle. And in case I will do it, I don't know, for a few minutes, I will get tired, and I can see this feature in the graph. So it's just the basic idea and the concept how it works. So I will move to another slide. Yeah, so to prove this approach is working, we create a 3 user study we are working. So first one was creating a battery of exercise. So we create some exercise which is easy, which you can easily do it in your home, and also other people can do it. And we did a measurement, and we make 30 videos with 30 probands. More videos, 30 probands, but many videos from each proband. So we have a lot of videos, so we can analyze it. So it was one user study. The second one was research we did with Charles University, with Faculty of Physical Health, and here we try to test function test and goniometry, and we measure it at 50 probands. I already did the measurements in CIIRC, so some of you participate in this study. So I'd like to thank you for participating. We just finished it a few weeks ago, and we will have some interesting results soon. So I will probably inform you next year. And the third user study is real-time application. We call it Office Stretch because it's like stretching in Office, and it's in progress. Because of the COVID, we weren't able to create the study because we wanted to start in offices, but it wasn't possible. So we postponed it, and I will talk about it later. So this study and this research is part of the project which we have with Ben Gurion University of the Negev. It's in Israel, and their side working on machine learning algorithms to work with the data and try to develop some machine learning algorithms, and at the same time they work on optimization of calculation, because the problem is OpenPose is very power consuming and also the performance, so we need to work with a lot of graphical cards, and they try to find some solution to work just only with CPU or just with some slow frame rate and so on. So it's their part of the research they are working on. So as a part of the research, last year we create an application. So we create a whole solution, so where patient can record himself as he exercises at home. Then the video is sent over the internet to the server. Then that is processed and then send the data and process about the exercise to the therapist, to the physiotherapist, and he or she can see the data from the physiotherapist. Last thing is the office stretch, is the application. So I will again show you a video so you will understand how it works. So it's me in my office. So I try to do some measurements, and I will stop it here. And you can see it's OpenPose, it's in real time, and I can see real time feedback. So for example, I see the video where some therapists or trainers show me how should I move, and I watch the video, and at the same time I'm capturing by the camera, and the data are processed, so I can get the real-time feedback, and I can see myself in the mirror, smart mirror, so I can see myself with the circles and this line. So for example, here you can see it's a circle around my knee, and it's because the angle is too open. So if I will run it, you can see I close the angle more, and the circle is getting smaller. So it's the way how we can let the patient or anybody know that he's doing the movements. I know if he's getting closer to the right position or not. And here you can see the green line. So it's just the line where you can see if your legs are in the right distance or not. So it's a visual feedback, and it's user friendly. And if you try to do few exercise, you can see it's very easy to follow it, and you can exercise according to this. So it's something which is already developed, and we are just waiting for when the situation will get better, and when install some units in the universities and let the people exercise, and then we will have some anonymous data and we can analyze it again. So that's it. Yes, and because of the COVID, we started with short survey. Maybe you remember I sent an email to whole faculty, and I sent some questionnaire. So it was about preventive rehabilitation at workplace. So maybe you fill the questionnaire, and in case yes, thank you very much. And in case not, maybe you can find the email by my name and fill it. So it would help us. So it's short survey about the design of the experiment. So if we will have some interesting data, we can still change the experiment we are going to do. So if you have time, so it's about 10 minutes, you can find the email and try to fill it. So this research is cooperation with Vienna University and also with Aarhus University in Denmark, and also Czech Technical. So it's joint research, and in the future we will have some competition between the universities, and we will design the study like everybody will exercise in their home university, and we will see the real-time data which faculty or which university exercise more. So it's part of the design, and I hope I will send you some information by email soon. So it's current status. So we have some publications related to this topic. So it's these two application, these two conference contribution, and because we don't have time, so thanks for your attention, and that's it from my side.
Thank you very much, Jindřich. And one short question, if there is any. It seems no, so thank you very much. Thank you all presenters from the COXIS department. And now I hand over to Professor Olga Štěpánková and BEAT department.
Hello, good afternoon. Let me invite you to meet my colleagues from the BEAT research groups. I will shortly present our group, and then I will pass the floor to my colleagues. So the group is rather small. You can see that it is well, it is a bit too small, isn't it? Yes. So this is an information about our group. I'd like to identify the main topics that we are working on. And well, here it is. Here you can meet all the team. The first line of names refers to the people who have the home workplace in CIIRC in our group, while the second line of names represents persons who cooperate with us very closely, but whose main home place is somewhere else. So they are part-time in our team. Well, the small team succeeded during the last year to publish 4 papers in international journals and presented 3 contributions, full-scale contributions at international conferences and 3 abstracts. At international conferences, the main ones are reviewed here. And here is the list of papers where we have been participating in preparing them. And now I think that the best is to ask my colleagues to present the basic results obtained during the last year. The first one will be Milan Niemi, who will be talking about his very good results related to early warning signs concerning Alzheimer's disease. Milan, floor is yours.
Thank you, Olga. I'll first try to share my screen. Okay, hopefully you can see my PowerPoint presentation now. Is that correct?
Yes, it seems.
Yeah. All right. Okay, great. So once again, good afternoon, everyone. My name is Milan Niemi, and I'm currently a PhD student under supervision of Olga Štěpánková. And today I would like to share with you some results from our studies, mainly on the topic of imaging in Alzheimer's disease. And since we are already working on this for quite some time, we've developed a few lines of research cooperations with Sweden, Germany, Spain, but also, of course, with, for example, Motto University Hospital in Prague, which are priceless cooperations, mainly regarding data source.
Sorry, Milan, I'm afraid not everyone can see whole the screen.
Whole screen, okay. Right. Okay, let me maybe. So what about now? Is it better? Okay. Can you see my screen now, like the whole screen?
I can see the whole screen. So. Yes, I see the whole screen.
It's both times okay.
Okay. All right, so I will continue, okay? Mm-hmm. Okay, so yeah, that was it. Basically, first of all, I would like to start with like the basic thing to have in mind, and that's I'm going to talk about Alzheimer's disease, and we have to have in mind that basically we have no treatment currently. I mean, like the ultimate treatment, we cannot really stop the progression of the disease, neither we can revert the changes with which have already happened. We can only treat the patient in a way that we can slow the progression. And there's this rule that the earlier we can detect the disease and start the treatment, the earlier, the better the treatment is. But unfortunately, there's no treatment for stopping the disease. So the early detection, that's for now the main goal. However, the ultimate goal, of course, is a complete understanding of the underlying mechanisms of the disease, and based on that, developing of the drug which can cure the disease. Well, so this is the paper which Olga talked about. It's the paper from last year, which we published in the Neuroimage. And the thing here is that we know that there are some parts of the brain, they are called cholinergic pathways or cholinergic parts of the brain, and we know that they are heavily involved in attention and memory. And we also know that these parts are very vulnerable in normal aging, but also in these pathological changes like in Alzheimer's disease. And so we know that, but it's very difficult to assess health of these parts of the brain in living patients. And therefore we use something which is called diffusion tensor imaging data. And we could look inside the brains like this in living patients, and using some advanced visual integration in vector fields, we are able to track these pathways in living people. And we showed that it is these pathways which we discovered, that they are the most sensitive and specific parts of the brain with respect to the attention and memory. So those were 3 goals which we had. So the first one is basically the modeling, which I described now, and of course identifying the parts of these pathways in healthy individuals to start with, and then to investigate how these pathways change in the Alzheimer's disease itself. So once again, this is a figure from the paper, which shows now the pathways in 2D. And yeah, once again, these pathways showed to be relevant in memory and cognition as we expected to, and they are the most sensitive and specific from all the parts of the brain. This is now the interesting part, because then we used this model in Alzheimer's spectrum. So this the third column here, this is Alzheimer's disease, and we can see that compared to healthy controls, we can see that the disease progresses in all parts of this pathway. However, we can look a little bit back to mild cognitive disorder, which is like a pre-stage of Alzheimer's disease. And we were able to show that developed by then, but we kind of expected these results. But what we were surprised is that we have also these patients with only subjective complaints. So those are patients, or just subjects who came to the hospital that with subjective complaints that that they feel that their memory worsens and they cannot do some type of everyday work as they used to. However, it's only subjective complaints because we couldn't see any changes in the standard MRI, or we cannot recapture these changes in standard psychological test batteries. However, with our method, we showed that actually there are changes already happening, like microscopic changes, and we can capture them, and we can see also where in the brain they are happening, and so we can really describe the pattern in which this Alzheimer's disease is progressing. So it's basically from the posterior part, from like the back of the head, and in the direction of to the frontal part. This is kind of a summary of this, and we can see that with progressing disease, with red being the healthy controls, and this purple is like the full-blown Alzheimer's disease, that the health of these tracks, these coronary tracks, is going really bad. I mean, we expected this, but we didn't expect to see such large difference between these healthy controls and the subjective cognitive disease. Okay, so this was like the main finding here, already in this stage, which cannot be currently objectively described. We can see large changes. Right, so this is the last slide where, and this is very nicely illustrating then when we compare Alzheimer's disease with healthy controls. Conventionally, we look at, for example, hippocampus, which is here the blue line, healthy controls from Alzheimer's disease, because hippocampus is kind of a benchmark structure to look at, which really loses its volume with the progression of the disease. But when we look at like the very early stages with these just subjective cognitive complaints, you can see that hippocampus really plays no role here, but it's the health of these pathways which we described with our method. All right, so those are the papers I was talking about. I think that's all from me. Maybe there's some time for questions, am I right?
Thank you very much for presentation. Well, there is a space for one question. If
yes, there seems to be a problem with the screen sharing. Somehow we see some email screen share, not the image, not the presentation.
Really? I'm sorry for that.
I think it's the screen of Profesorka Štěpánková, not the screen of Milan Němý.
Okay. Yeah.
We cannot hear Profesorka Štěpánková.
Olga, your mic. It's off.
Olga, unmute yourself.
Sorry. Well, if there is a question, please ask the question. And in the meantime, I'd like to invite Mr. Mužík to get ready with his presentation. It seems that there are no questions, so I'd like to pass the floor to colleague Mužík, who will be talking about wearable sensors and the review they have provided. Thank you.
Good afternoon. I would like to shortly present an article we published in Journal of Medical Informatics. It's called Wearable Sensors with Possibilities for Data Exchange, Analyzing Status and Needs of Different Actors in Mobile Health Monitoring Systems. It was a result of our mixed Czech and Norwegian team. We already cooperate nearly 10 years, and this is one of the results. We published the paper in January last year. And together with this article where we present the results, we also published a complete data set of all data and all attributes. It's quite a huge table. It's also completely freely available in the second paper on this screen. So what we did actually, the motivation for this review was that there is an increasing number of wearable devices with remote data transfer ability. The wearables are a useful source of medical data that we can get from patients' daily life. The most common sensors are for physical activity, for sleep tracking, for heart rate monitoring, thanks to photoplethysmography, for blood pressure monitoring or blood glucose level monitoring. But the recent development more focused on miniaturization and addition of new features and much less on standardization and interoperability. In this picture, you can see some examples. This is the smart ring for monitoring of sleep and heart rate, smart gloves. This is the insulin pump connected with a continuous glucose monitor. It's also a wearable device because it's all the time connected to human's body, or most of the time, and the most common smart bracelet for physical activity monitoring. The objective of this research was to review existing wearable devices, to categorize the technologies and capabilities of these devices, to identify proper attributes for classification, and summarize the perspective from main stakeholder groups and definition of these groups. In this review, we focused on wearable devices and their ability to exchange data and to have some interoperability capabilities. And all this was done as an activity part of the full flow research project, which was focused on investigation, how to integrate and utilize data between three main actors in healthcare: patients, primary care doctors, and secondary care actors. So we reviewed the database and internet sources. The main source was the public OneRecord database. We identified 13 attributes focused on data exchange. We marked them A to M, and those were focused on a communication interface, data protocols, integration to health platforms, and data accessibility. We also identified three main user groups or stakeholders of these devices. These were electronic health record providers, those companies that create systems for collection of medical data and their presentation to doctors. Second group was software developers, the developers who develop mobile application for data collection, processing, and transformation. And the third group were patients or users of these devices. The main source of data for us was the OneRecord database. It's the public database of wearable devices, not only medical devices, but we picked medical or wearable devices focused on medical data. It's maintained by private OneRecord Canadian company. It has more than 1 million searches in this database annually, and currently has 431 devices from 266 manufacturers. The result of our review was this generalized flow of the information. I won't go into detail, but in general, there is a user source of the data. It sends the data either to the wearable device or device cloud service via the mobile phone, or device cloud service via API via mobile phone. In this case, the data can be sent to health platform, which is in most cases Google Fit API or Apple Health Kit API. And from there, data can be sent, shared to either third-party fitness services that can send the data into middleware applications. And from these two, data can be shared to electronic health record, which was the main interest for our search. We get 310 devices from OneRecord database and 52 devices from other sources. We identified 13 attributes. I won't go to detail, but some of them were like what type of wearable system it was. Was it either smartwatch, insulin pump, prostheses, gloves, smart glasses, and so on. Second was the communication interface. In most cases, it was Bluetooth, but we also found Wi-Fi, NFC, and some proprietary radio interfaces. C was the data protocol, if the device either used Bluetooth low energy or some proprietary protocols. D was if it connected to smartphone or PC. If there was a direct integration with the health platform, Google Fit or Google Health, if there was an integration with third-party platforms like Strava, if the device was able to connect to some middlewares like a Gluco, Tidepool. H was the health data tape. It was usually physical activity, heart rate, so, oxygen saturation, and so on. I identified the integrated sensors, the GPS, accelerometer, blood pressure sensor, and so on. J was if it was certified as a medical device, if it was either certified by the FDA or it had CE mark, or it was uncertified, which was in most cases. A K attribute was focused on user data access if the user either had access to data via Bluetooth or REST API, or in most cases, user didn't have any direct access to the source data. L was focused on developer access, and M was availability of device. It was either in production, marketing, scam. In some cases, device was presented like that it existed, but in fact, it didn't exist. So we also focused on this attribute. The results, we identified main perspective for three stakeholders. First were the developers on mHealth enabled application, mostly mobile application, and mostly or very often they must rely on associated cloud services or aggregators and health data platform. Developers in many cases do not have direct access to the data from wearables. For the health platform providers, the critical features were data reliability. For example, last year there was there appear many devices with photoplethysmographic measurement of blood pressure, like bracelets that measure blood pressure. But reliability or accuracy of this measurement is very problematic. There is not even a validation protocols for these devices. And also the problem is the certification and the risk in data transmission. There are some initiatives like FDA digital health software pre-certification that may help these to resolve these problems. For patients, the wearables are very attractive. There are more and more features added each year to these devices. In 2019, there was a boom of blood oxygen saturation measurement from the bracelets, and the last year was many devices added possibility to measure blood pressure. It simplifies data collection in chronic diseases because it measures data from patients all the time, but patients need to be aware of limited reliability of mostly uncertified devices. And the last slide, the results. We identified these challenges that there are only few CE mark or medical certified devices, or class 2+ medical devices or FDA certified devices. Most of them are classified as the wellness devices, so shouldn't be used for making medical decisions. Only few devices implement Bluetooth low energy gut profile, which is de facto standard for transmission of medical devices from wearable devices. And most devices therefore use proprietary or closed communication protocol that doesn't allow normal users or developers to access the data. Only few systems support health middleware. 37.5% of devices provides user access to the source data. So it's not really all devices enable patients to get access to their source data to export them so only 16% of devices provide direct access to the source data. That's mean without the use of manufacturer's cloud. In some cases, developers really need direct access without need of internet connection, and only 16% of devices provide this. And lastly, the increasing data ownership awareness will also push manufacturers to clarify secondary use of data. That means that many manufacturers use or sell the data, and they do not publish any information what they really do with data that actually belongs to the user, to the patient. So that's all from me. Thank you for attention.
Thank you very much. And the last talk will be presented by Jaroslav Cibulka and Denis Özdemir. Please, floor is yours. And of course, at the end, we can ask questions to Jan Mužík, or he will be certainly open to address all your questions provided by email. Thank you.
Good afternoon, everybody. Do you see my screen?
Yes.
Super. I'll just turn it on. Yeah, okay. So me and Denis would like to present our work about low-cost PETbot grounded in a smart home IoT as a source of interventions for people with dementia. So we have a published review article summarizing current use of assistive robots for people with dementia, both pet-like and humanoid robots. We have further discussed the drawbacks, for instance, low deployment, especially due to high cost, limited language mutations, and so on. Another drawback is, for example, the low-cost robots. They are not really smart. They are still rather toys. There is a lack of comprehensive studies. The integration with smart home IoT is still poor, and the data security is missing. That's actually the part which Denis will be talking about. There is no guidance how to use such robots in this elderly care environment, and that means that the users, like caregivers or the patients with dementia, they are losing the interest in using this robot. So, so we think that RoboPet, our idea is that is expected to be much easier to comprehend. We promote more or wider user involvement in the design process, and we want to list risks and misuses of IoT vulnerabilities, including their remedies. So the conclusions of this review further shapes the key points of our project. So that is participatory design, the affordable and low-cost design, focus on daily life challenges, focus on modes of communication, using the smart home IoT data, and to provide tailored interventions. And we also want to conduct experiments to evaluate users' acceptance and attention. So here's the overview of our system. Let's think about some typical scenarios for people with dementia. For instance, people with dementia repeatedly ask the same question. Let's say, when is the lunch? And so the PETbot will listen. He has got the offline speech recognition, and the question goes via the Bluetooth Low Energy to the Smart Hub, and the questions continue via the LTE to the master server, where actually the caregiver upload the schedule and current food menu. So the answer can go back to the PETbot, and PETbot can answer these questions. Of course, the PETbot can remind about the lunch without questioning independently, and also can remind about washing the hands before the lunch, for instance. And such questions could be also regarding taking the pills or family visits. Next scenario could be that the user can forget different habits, for example, washing hands after coming home. So the smart home IoT sensors will detect there is no presence in the bathroom, and that goes to the Smart Hub, this information. And in the Smart Hub, there is a JavaScript running which will detect that some events were not completed and send a warning to the PETbot, and PETbot will say, for example, please wash your hands. Another scenario could be deviations from typical behavior. So for example, frequent visits on toilet. So the smart home IoT again will detect there is some frequent or often presence on the toilet and send this message to the smart hub, where there is a running inference of neural network. And this neural network was trained on a master server. And this inference will lead to detect of deviations and again send a warning to PetBot, and PetBot will say, you were on toilet so often today, let's call a doctor. Another or last simple scenario is when the user is sad and ask a PetBot for some entertainment or some activity. So the PetBot can, for example, play the REM-book, which is our application for tailored reminiscence therapy. So that can run on the screen. Regarding the PetBot itself, I don't want to go into much details, but I decided to use Arduino board, which is called Arduino Nano 33 BLE Sense, which is pretty compact and full-packed low-powered board, together with the dedicated speech recognition, offline speech recognition board, which is called EasyVR 3 Plus. And I haven't seen such a combination yet. It's very compact. It's very low power. It needs requires some extra coding to be up and running, but it's a very promising solution, and so that's what I have chosen. Regarding the smart home data model, for example, this is the description of how we want to approach acquisition and processing of the smart home IoT data. So we rather focus on continuous snapshots of the whole household. We're not do the standard way as usually goes for the sequential data. So we are doing real-time continuous snapshots in order to create a behavioral model, and that means we will be able to detect deviations from that typical behavior. Regarding the unexpected behavior or unexpected events, for instance, like I said about the forgetting washing hands. So we have such a data structure, and this one is specifically for the forgetting washing hands after coming home. So this data structure serves for the detecting and warning about unexpected behavior. Okay, that's from my side, and I will hand it over to Dennis.
Thank you, Yarda. Can you hear me well?
Yes.
Okay. So my name is Deniz Özdemir, and today I will continue with the security and privacy implication of Internet of Things. So during our research, our literature review, we have analyzed that and came to a conclusion that the architectural security mechanism, both software and hardware-wise, is currently missing. Basically, comprehensive and mature security standards, guidelines, and principles are not widely prepared. So most importantly, specifically enhanced and applied to social robotics with respect to people with dementia. Hence, a tailored scheme for network and application security principles are not studied widely. So we would like to focus on applicable vulnerabilities and remedies for our work. So in order to deploy a functional up and running smart home environment, it's crucial to take into consideration two major elements by design, and they are security and convenience. Hence, for implementing a robust architecture, a secure communication channel must be deployed between smart healthcare devices to the database, and ensuring a proper risk assessment is in place with a strong privacy. Because as more and more smart home IoT devices came into surface and became more seen by the malicious actors, then motivation for compromising such instances grew exponentially. Since one of the well-known attacks are denial of service or smart home camera hacking, since it happened with Mirai botnet and lizard stressors and so on. If I give some examples, with the attack scenarios in home environment can bring its own calculated risks and challenges that are not uniquely present in traditional computing mechanisms. Some unique attack vectors include, for example, allocating the location of the camera feeds and other costly devices, vulnerable cyber-physical logs prone to electronic compromise, checking if the home is occupied or not by using the camera, microphones, motion sensors, logs for lighting, door locks, pressure sensors, and so on. If the malicious users try to interface with the workings of such a technological advancement and tampering the data of the healthcare technologies to harm the user by changing the treatments, notification, and even launching distributed denial of service attacks, eventually the malicious entity can also take over control of the whole Internet of Things devices, either to elevate privileges, to attack further systems, or simply make the user and the household vulnerable. So during our research, we found out that it's paramount to drop a scheme where it contains probable attack vectors for robotic systems in healthcare settings, especially considering the fact that the applications are sensitive to location information of the patient with respect to acute situations and the status of the health condition, which is immensely crucial to consider for aging and patient care. So to start with, the very first initial defense mechanisms shall be set to create a layered infrastructure, security, and defense in depth for the interconnected network components, which include intrusion detection and prevention systems with a set of custom rules and commands specifically targeted to design trustworthy and human-centric artificial intelligence. As a core challenge, we have identified the development of robust and trustworthy systems which are capable of comprehending us as humans in order to adapt the complex environments and situations and react accordingly. So we can go to the next slide, please. So with our research, we have found several key points to consider to study. First of all, the mutual authentication scheme must be implemented in order to allow the whitelisted and authorized users to have access to the confidential data of the smart device. Furthermore, after mutual authentication is achieved between trusted parties, a session key management protocol shall be initiated so that the transmission of data should be encrypted using the shared session key. Furthermore, the user anonymity and untraceability and other aspects of the security functionality of the authentication mechanism of the smart home aspect should be studied. And another crucial point is to consider the clock synchronization issues in security, because the timestamp functionality shouldn't be omitted when it comes to healthcare to detect unauthorized login attempts or wrong password information, so that this type of attacks will not be used to create some data loss, replay attack, privilege of escalation, or user impersonation attacks. So next slide, please. Therefore, it's critical to address the network traffic flow between these interconnected devices, the network systems, to analyze the patterns of malfunctioning and the specific traffic patterns, not only to understand the behavior of the intercommunication between those devices, such as tracking services, sensor operation, and transmission systems, to ensure the physical security is also managed properly, but also to set up the necessary in-depth security architecture that is robust and resilient to the attack vectors that I described earlier. Last but not least, information security principles should also be integrated to be able to interoperability and the integrity of the data.
We have to be quick.
Okay, that it was almost my last two sentences. So the last slide, please.
It's actually the last one, I guess.
Yes.
The last one.
So as a conclusion with our literature review, we have came to the conclusion that the assistive robots are not widely adapted due to the pricing factor, and the security architecture of companion robots shall be studied distinctively. So with our research, a low-cost RoboPet companion, we would like to focus on these aspects to improve this together. And this is the end of our presentation, and we are kindly open for your collaborations, and thank you very much for your time.
Thank you very much for nice presentations.
Thank you.
And of course, we are open to address all your questions via email if you are interested in something more.
Okay, so Olga, thank you very much for presentation of your department. I hope that everybody enjoyed the meeting. And as I said, it will be put on YouTube because it was recorded. And I hope that we will meet next year in person, not like today, over Zoom or over Microsoft Teams, sorry. And that we will spend some time in enjoying being together. Thank you very much for assisting and have a nice day. Bye-bye.
Thank you. Bye-bye.